Okay, so when we left off last time, we had just completed some very brief exploratory data analysis of our Spotify song attributes dataset from Kaggle. And so just to recap, this dataset was a list of a user's songs that he provided that were labeled with a target value of 0 or 1 depending on whether or not this user liked or disliked a particular song. And then our features were a number of different attributes that were in some cases discrete values, for example the key that the song was in, or continuous values such as the duration of the song, and then some of these other features that Spotify extracts, for example the danceability, energy, loudness, these sort of qualitative attributes that Spotify has found a way to attempt to quantify. And so we went through and we produced a series of histograms that were split on that target value of either liking or disliking a song, and then we looked at the distribution of values for that particular feature. So in the case of our continuous features, or our features which had continuous values, we get a sort of distribution. And we can see that there is actually some structure to the data, so it's not looking totally random or totally noisy or anything. In fact, we notice that this user appears to have a slight bias for liking music which has a slightly higher danceability value, and a slight bias for disliking songs which have a slightly lower danceability value. Of course, there's some overlap there. And we see some similar types of structures here for each of the different attributes, so that's pretty interesting, especially when you think about the fact that this user isn't necessarily thinking about any of these attributes explicitly, certainly not in the way that Spotify is calculating them. Spotify just has a sort of algorithm that is calculating these values for danceability and loudness and valence and energy and things of that nature. And it just so happens that this user's preference for the songs which have these attributes actually has some structure, so that's pretty interesting. So in this video what we're going to do is we are going to build our first machine learning model, and we're going to implement a decision tree classifier. So I'm going to go into more detail about decision trees in general in a separate video where I'll actually draw out some more visuals and kind of go into more details about the specific nuances of decision trees. But in this video we are just going to go ahead and build one for this data set and use it to see if we can predict whether or not this user would like a song that is from the test set based on data that we trained it on from our training set. And if you recall from the last video, we used scikit-learn's train test split method here in order to very easily select our tests and our training data. And so it's going to randomly select data from our total data set and then split it out into 15% test data, and then the remaining 85% will be used to train upon. Okay, so we'll go down to the bottom here and in the last cell. So I've just started this here where we have this variable c, and we're setting it equal to a decision tree classifier, and then I'm going to pass it this param min sample split equals 100. And so it helps to understand what a decision tree is here to understand this min sample split. And as I said, I'll go into more detail about the specifics of how decision trees look and how they kind of work in more detail in a follow-up video. But the thing to keep in mind here is that what a decision tree is doing is it's essentially asking a very specific set of questions about the data set that it receives. So it will say things like, maybe at the top of the tree it will say, is the danceability of this song greater than or less than 0.6? And if it's less than 0.6, then it's going to ask another question, is the valence greater than or less than 0.7 or 0.8 or something. And so it's gonna create a bunch of leaves, just like a tree would kind of fan out, asking new questions specifically about whether or not a particular feature had a value that was greater than or less than some threshold. And then it's going to split on that node and produce a number of different leaves. And so in our case, we're going to say the minimum sample split. In other words, the minimum samples that are required to split one of those nodes is going to be 100. So if we were to make this as fine-grained as possible, in other words, just 2, so that we had one observation on either side of a split, then we would have this extremely dense tree with, in this case, probably hundreds of leaves. And so a decision tree that is overly specific to the data set that it's trained upon is at a very high risk of being overfit. And again, I'll go into more detail about what all this kind of means and its implications in a follow-up video. But you can kind of think of an overfit model as being too specific to its training data, so that when it sees new data, its prediction error on that new data is at risk of being very high, because after all, each of these songs only share some sort of broad structure. You can kind of think of an overfit model as being one that is too closely predictive of its training set. And so when we feed it a piece of training data, essentially it might even just perform like a lookup model, so that it would quote unquote, predict any individual instance of its training set with perfect accuracy. But when it saw something new from the test data set, then the risk of it having a very high error when predicting from that test set is going to be very high, because we've essentially gotten too specific about the attributes of the training data. We want to be able to say something general about our data set, and we don't want to get so specific that our model overfits to some particular training data. So there are all sorts of ways to sort of calculate statistically optimal values for some of these parameters. We're just going to kind of stick with a nice even number here, 100, and just to take a look back at our test set, or the size of our training set, we can see that our training set contains about 1700 values. So we're going to say that minimum sample split in a particular region will be 100 observations. If we were to use the minimum value here of 2, then our tree would be, I think, overly complex and probably overfit. So I'm going to go ahead and Shift Enter to run that. And if you get an error here that the decision tree classifier is not defined, then just head back up to the top of your notebook and make sure that you go ahead and run your import cells again. That's going to apply if you've since shut down and reopened your notebook since the last time that it ran. And you're also then going to want to make sure that you go ahead and import the data and that you run your test and train split. So in fact, what I'm going to do is just go ahead and run the whole notebook, and we can do that by clicking on kernel, and then we're just going to restart and run all. And then I'm just going to go ahead and say OK here. And so it's going to go ahead and run everything. And now when it's also run our decision tree classifier here, and we've stored it in this variable C. Okay, so now I'm going to define a set of features that we want the decision tree classifier to consider as it's being built. So I'm going to store that in a features array here, and we're going to make sure these correspond to the actual feature names that are in our data set here. And we can see those in our table here that's provided by Pandas. And so you can see we have each of the column headers here actually corresponds to a particular feature. And then target, of course, corresponds to the 1 or 0 depending on whether or not the user liked a song. So we'll come down here. So let's train on danceability, loudness. Go ahead and do all of the ones that we looked at here. Valence. We're just going to go ahead and fill this out for all of the other features that we took a look at in the last video. Okay, so I've stored that as a list. I believe I said array earlier. I'm switching too often between JavaScript and Python. And then what we can do is we can define our training set here with xtrain. And this is going to be from our Pandas data frame. We're just going to select all of the features. And so now that I've defined these features here, I can just select them from our training set using this syntax, which is Pandas. And then ytrain, which is going to be the target value from our training set, will just be train, and then we'll just specifically select the target column. Likewise, we'll go ahead and copy and paste these two, and I'm going to do the same for our test set here. So we've got our test data frame from which we're selecting the same features, and our test data frame selecting the target values. So I'm going to go ahead and Shift Enter and run this. And in fact, if you take a look, for instance, let's look at the target values from our test set, for instance. This is actually just going to be a Pandas series of 0s and 1s, depending on again, whether or not the user liked the song. So I'm going to go ahead and DD to delete this cell. And so we've got our classifiers. Let's build our actual decision tree. So if I say DT, that's what we use to store our decision tree. We just call fit on our classifier. So we'll say c.fit, and the first param that we pass it is going to be xtrains. That is the values for our features from our training data set. And then ytrain, which is of course our target, and we'll shift enter here. And so just like that, scikit-learn has actually just produced our decision tree. And so one way we can visualize that is by writing a method that will actually produce an image using graphviz. And so I'm going to write that here. I'm going to just call it show tree. And we're going to pass it 3 params here, a tree, the features, and then a path where we can write the image to disk. And so our file, we use Python's IO, and specifically string IO. And then we're going to use export graphviz. And this is coming from scikit-learn. And we'll pass this method tree, and then we'll set the out file parameter to our file. And then we'll say our feature names are just our features list. And then we're going to use pydotplus. This would be something that would definitely have changed from Python 2. So again, you're going to want to make sure you're using Python 3 if you're following along with this series of videos. And here we have a method graph from .data. And we're going to call getValue on our file. And then here we can actually call writePNG, and we'll write it to the particular path that would provide the showTree method. Now we're going to be using a library called scipy, which should have been imported here at the top of our notebook. And we're going to be using misc for miscellaneous, I presume. And this is going to give us access to an imRead method, or an image read method. And we're going to pass that, again, our path. And imRead is pretty cool. It's actually going to read an image from a file as an array. And now we're going to use matplotlib to just simply plot out that array. So we use plt.rc params, from which we're going to select figure.figsize, and this is going to allow us to change the default size of the figure that we're going to display in our notebook, and we'll set it to 20 by 20. We're just going to say plt.imshow to show this image array that was provided by scipy when it read the image path that pydotplus created for us. So that's our method. I'll go ahead and shift enter, and now if we call it showTree and we pass it our tree, which is DT, our features list, which we defined here, and then just any file name that we'd like to write it to. So I'm just going to call this decision tree 1.png, and shift enter there, and we got an error here. So RC params just had a typo in it here, so it should be figure.figsize. Let's go ahead and see if this works. Shift enter twice. And yeah, so you can see that it has created our decision tree for us, and this is a visualization of what's actually happening in this tree. And in fact, if we go to the location where this project is running on disk, in projects, in my case, ML, and then Spotify, here's one that I ran earlier, and here's the one that we just ran. So if we go ahead and open this up, and so you can see that in fact the first question that the decision tree is asking is whether or not the instrumentalness is less than or equal to 0.0001, and you can see that the total number of samples is indeed our training set. So we have 1,714 samples to begin with. And then whether or not this is true or false, then we go down 2 sort of very broad branches, and then we get more and more leaves to complete our entire tree. And you can see that anytime we have a number of samples that is greater than 100, which was our minimum split value, it's going to go ahead and split that population based on some other question that it's asked here. So yeah, this tree is pretty straightforward. One of the nice things about decision trees is that they are actually interpretable. In other words, we can actually look at the process that the model has used to classify whether or not a user liked or disliked a particular song. In that sense, it's much different than a neural network or any reasonable neural network classifier, which is more like a black box. So it's very difficult to, in fact, quite impossible to interpret the interactions between nodes and how they have an effect on the outcome in a deep neural network classifier, for instance, where in this case we can look at any of the nodes in this tree here and see explicitly the decision that is being made to classify a song into one or the other value. So that's very nice. And another advantage of decision trees is the fact that we had to do very little preparation of our data. And in fact, if you think about it, our data has different sort of types, if you will. For instance, most of our features have continuous values. For instance, loudness and duration and speechiness. They all go from 0 or some negative number to some positive number along some continuum. Whereas our feature for, say, key, for instance, was discrete, so we had 12 possible values for our key feature. So we didn't have to do anything special to prepare our data. We just had to provide a set of observations that contained values for each of them. And so so we've produced our tree, and now that we've visualized it, we can just continue to use scikit-learn here to implement it. And again, that's going to be very straightforward here. So we'll have a y prediction, and we're going to use the same classifier. And instead of fit, we're just going to call predict, and we're going to pass that x test. So that's the values for our features from our test set. So go ahead and I'll shift enter here to run that cell. And what this produced was an array of ones or zeros. We can look at that if we just call y predict. And so this is the prediction. So it looked at our test set. It took a peek into each of the values for each of the features here, and then it ran this very straightforward algorithm that just involves saying yes or no depending on some feature that it saw in our test data until it classified it as a 1 or a 0. And it did that again on a decision tree that was built on training data. So we didn't see too much structure to our data, so we probably shouldn't see a very high level of accuracy yet. But let's take a look at what our accuracy actually is. We could manually, of course, compare the arrays, our y predict array here with our y test array. We can actually, once again, use scikit-learn to do that for us. So I'll go ahead and make another import here from sklearn.metrics, import accuracy score, accuracy underscore score. And then we'll say score is equal to accuracy score, and we'll just pass it y test, and we'll also pass it our y pred. Just multiply that by 100, and then we can just do a simple print statement here, and we'll say accuracy using decision tree, and then we'll go ahead and round our score to 1 decimal place. We'll go ahead and see what that was. Oops, and we got some invalid syntax here, because I didn't put a comma for our first string here. And so we got 74.9%, so just below 75% based on a very simple model, just a very straightforward decision tree model. So that's actually not too bad. I mean, it's not a fantastic classifier by any means, but as far as one of the simplest types of machine learning models that we could implement, it actually doesn't perform horribly anyway. Now, just for fun, let's see what would happen if we were to, say, change our min sample split value here. So say we were to make this much smaller, or why not just set it to the minimum value of 2. So we'll go ahead and run this. And now let's see what happens when we draw this tree. So here we'd expect to see a much more dense tree with many more nodes, of course, because it's going to continue splitting our samples down until it gets the smallest possible split between values. So you can see this enormous tree we have here, a very elaborate model. If we go ahead and take a look in our folder now, so this image is just enormous. Of course, it's still interpretable, if you will, but it's much more complex. And that's simply because it's asking more fine-grained questions of the data in order to split it into the minimum possible number of samples as an output. And essentially what this is it kind of serves as a lookup table for our training set. So if it were a perfect decision tree and was somehow able to split out our samples into buckets where we had exactly one sample at the end of each leaf, in each leaf at the end of all of its branching, then we would have a lookup table. Here we have something that's probably very close, because I do see a lot of buckets with 1 or 2 or 3 samples in them. And in a lot of cases, we do have like 1 sample. And so again, the goal of machine learning is not to build lookup tables. It's also not to be able to predict data for values that we already know, of course. And in fact, I would expect this to perform worse on our test data. So let's go ahead and run that. And so yeah, performs slightly worse on our test data, though only by about 4%. So that's it for this video in terms of building a simple decision tree classifier for this user's Spotify data. If you'd like to see how we did the exploratory data analysis bit, go ahead and take a look at the previous video in this series. And if you need to get the data, just head over to Kaggle, where you can download it, and you can also take a look at the user who submitted this data also provided some code to show how to grab the data using the scipy library, which is a Python library for interacting with the Spotify API. And go ahead and give this a shot. I may take a look at this in a future video to query my own Spotify data. So yeah, that might be kind of a fun project. And in the next video in this series, we will look at improving our classification model by implementing a random forest. And that should help us address some of the potential overfitting issues that we have with our decision tree classifier. So thanks for watching, and if you do create your own classifier for your own Spotify data, I'd really love to hear about it. Be sure to mention it in the comments below, and let me know if there are other data sets that you guys have come across you'd like to explore using machine learning as well. Alright, thanks, and I'll catch you next time.